So what we're going to find are the volumes of three-dimensional objects, and you're going to have to imagine them. What we're going to draw on the paper is two-dimensional, and that's going to be the base of the object. And then what's going to happen is these shapes, you're going to have to imagine them popping up out of the paper towards you, kind of like a pop-up book. Do you remember when you were a kid and you had like a book, you opened the pages and things like popped up out of it at you? You're going to have to imagine these shapes popping up out of the paper at you to create this three-dimensional object. So I have some pictures of some of these to help you visualize. So like for this first one here, the base is circular, and that's what we would draw on the paper. And then you have to imagine these triangles coming out of the paper towards you, these cross sections that are triangular, and it would create this shape, looks like sort of like a paperweight, I suppose. And we're going to find the volume of that. Isn't that cool? That's so cool. Here's another one. The base of this is circular. So again, that's what we would draw on the paper, is that circular base. And then the shapes that are popping up out of the paper are rectangles. And so it creates a three-dimensional object that looks like this. This is how 3D printers work. They print like a slice of the object at a time. So it's just cool. It's neat. I like it. There's lots of geometry in it. But you have to turn your imagination on and to imagine these three-dimensional objects, because I don't physically have them here for you to see and hold and touch. So you're gonna have to imagine it. Okay. So come on this journey with me. All right, now, what's nice about these ones is they will come out and tell you if it's a dx or a dy problem. With the area problems, do you remember I was like, people always ask me, how do you know if it's dx or dy? And I'm like, well, I know you're not going to like the answer, but you kind of just have to look at it, see what you've got. Is there an upper graph and a lower graph, or is it sideways? These ones will come out and tell you. If it says cross sections are perpendicular to the x-axis, it's dx. If it says cross sections are perpendicular to the y-axis, then it's dy. That's the one kind of nice thing about them, is you don't have to wonder. Like the problem is going to just come out and tell you. And remember, as soon as you realize it's dy, you have to rearrange the equations so that they are x equals. The whole thing is going to have to be backwards. All right, here we go. The base of a solid is bounded by this graph, the x-axis, and the y-axis. And we're going to stay in the first quadrant for this one. All right, so first let's graph this. It's going to be a parabola, and it's upside down because of the negative, and it is moved up 1. This is 1 minus a fourth x squared. So I'm going to have the point 0, 1, and then let's try and get a few more points. Let me try plugging in 1. If we plug in 1 for x, we're going to have 1 minus a fourth, which would be 3/4, so like right about there-ish. Same point on the other side because it's going to be a parabola. And then if we do 2 squared is 4. 4 over 4 would be 1. So we'd have 1 minus 1, which is 0. So that's going to be 0 there. And our graph looks like this, an upside down parabola. And then it said the x-axis and the y-axis. So I know it's like, which side of this do you want? It actually doesn't matter because there's symmetry. But if you get a choice, pick the positive one. It's just a whole lot easier to deal with. So we'll stay in the first quadrant for this. Also, because I'm your teacher and I just said so. We're going to use this area. So that is the base of the object. So let me pull out that picture we were looking at. Like this one is circular. Like we drew the base. You're going to have to imagine the shapes that are coming up out of the paper. This is just the bottom of this three-dimensional object. Now, this says that our cross sections are squares perpendicular to the x-axis. So you've got an infinite number of squares that are perpendicular to the x-axis, all sliced up like that. And you have to imagine them coming out of the paper at you like this. All right, so here's what I always suggest everyone does. Draw your shape, in this case, a square, off to the side. And I use color coding for this. So I don't know if you have a highlighter or a different colored marker. I just feel like it helps. What we're doing is we're taking one square out and setting it aside. Kind of imagine like a loaf of sliced bread, and you're going to take out one slice and set it aside so that you can sort of examine it. Like you took a slice out of the loaf of bread. The base of your shape, in this case a square, is going to match up with this slice. Here's what I always get asked. Ms. Cole, why did you draw that right here? it doesn't matter. It's arbitrary. There's an infinite number of them. I could have, I could have taken this slice or this one 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 or this one. There's an infinite number of them. It's just this is going to match up with the base of the shape. So since they said perpendicular to the x-axis, it's going to be a dx problem. And the base of this shape is upper graph minus lower graph. So it's just like we did with the areas. It's either going to be upper minus lower or right minus left. So if we do upper graph minus lower graph, the upper graph is this parabola. The lower graph is the x-axis, which is just 0. So you can pretty much ignore that. And so the base of this square is 1 minus 1/4 x squared. So that is the base of our shape. All right, now we're ready to set up the integral. We're going to integrate, this is dx, so we're going to integrate using x values. So it's going to be from 0 to 2. And what goes inside the integral is the area of your shape. So they're all going to be shapes that you know the area formulas of: squares, rectangles, semicircles, triangles, stuff like that. There's not going to be like a pentagon or something. This a of x represents the area. So we're going to do the area of this. So hey guys, how do you get the area of a square? Because that's what's going to go inside of here. How do we get the area for a square? Yeah, square it. It's base times height, right? So if this is a square, if the base is this 1 minus 1/4 x squared, the height is also 1 minus 1/4 x squared. So you're going to take that and square it. All right, now I am going to work this out by hand. All right, so what I'm going to do is write that twice. If it's squared, that means that we have 2 of them. So I'm going to write that twice. It's going to be a little bit of writing. You're all going to be okay. It's like a little bit of algebra here. And then we're going to multiply that all together. So everything is going to get distributed together. So 1 times 1 would just be 1. And then I always do the outsides and insides together because they're going to combine. The outsides are going to give you minus 1/4 x squared. The insides are going to give you minus 1/4 x squared. So if you minus 1/4 and minus 1/4, that would be minus 1/2 x squared. And then multiplying the last. Negative times a negative is going to be positive. 1/4 times 1/4 would be 1/16. And x squared times x squared will be x to the 4th. All right, so we just had that algebra of distributing all of that together. Now it's antiderivative and then upper boundary minus lower boundary. So antiderivative is going to be x minus, now ignore that 1/2 for a second. This would be 1/3 x cubed. But since there is a 1/2 there, 1/3 times 1/2 would be 6. So 1/6 x cubed plus, I know, same thing here, ignore the 1/16. This would be 1/5 x to the 5th. Oh, I'm sorry. Copy error. Thank you. Someone just caught that in the chat. Copy error. Copy errors are the absolute worst. For you know exactly what you're doing and you just copied to the next line wrong. I'm sorry. Copy error. It should be a 2. All right, so ignore this 1/16 for a second. This should be 1/5 x to the 5th. But there is a 1/16 there. So 1/16 times 1/5 will be 1/80. So 1/80 x to the 5th such that 0 to 2. So it's antiderivative, and then we're going to do upper boundary minus lower boundary. Probably going to end up leaving this one alone because this is going to be sort of nasty here. Plugging in 2, that'll be 2 minus, all right, 2 cubed is 8. So that'll be 8/6. I realize that reduces, but I think I'm going to stop with this one. 2 to the 5th would be 32. So this would be 32/80. Again, I realize that reduces as well, but you get to a point where it's like, how far are we going to go with this? If you plug in 0 for all of these, you're just going to get 0. So I'm going to go ahead and stop there. If it's free response, you can just stop. If it was multiple choice, you'd have to fight your way through those fractions, get a common denominator and add them together. I'm not trying to torture you though, so we'll just go ahead and leave that one there. All right, let's try another one. I tried to do an example of like each type of shape here. All right, number 2, the base of a solid is the region bounded by one arch of y equals sine of x and the x-axis. So this one, I'm sorry, we're gonna have to like fix the labels on the x-axis. We can't count by 1, 2, 3. We're gonna have to count by pi over 2 because we're gonna graph a trig function here. So this should be pi over 2 and pi and 3 pi over 2. Like we should be counting by pi over 2 there. So sine of x is going to start at the origin and then wave. So we'll be up here at 1, back down to 0, and so on and so forth. It's going to do something like this. Right, so it says we're going to use one arch of this. So, pick the positive part. We're going to use this one right here. And the x-axis. So this is the base of the three-dimensional solid that we're creating. And you have to imagine these shapes popping up out of the paper towards you. So it says cross sections are equilateral triangles perpendicular to the x-axis. That means it's going to be a dx problem. All of our triangles are getting sliced up this way. It's like you have this slice of bread. It's triangular though. These triangles are coming up out of the paper towards you. So hey guys, what does equilateral mean? That's a vocabulary word in here. What is an equilateral triangle? Yeah, good. All the sides are equal length. So all the sides and all the angles are the same. So what I always suggest doing is take your shape and draw it off to the side. So here's an equilateral triangle. And because this one is a dx problem, the base of our shape is going to be upper graph minus lower graph. Again, I always get asked, Ms. Cole, why did you draw your highlighted part there? It doesn't matter. It's arbitrary. I could have drawn it anywhere in here. There's an infinite number of triangles. We have an infinite number of slices. All right, so the base of that is upper graph minus lower graph. Again, it's going to be just like the areas. It'll either be upper graph minus lower graph or right graph minus left graph, right? Just like we did last time. Which this would be sine of x minus 0, which is just sine of x. All right, so now we're ready to set up our integral. So we are going to integrate from 0 to pi. And inside of there, we're going to put the area of our shape. So area for a triangle is 1/2 base times height, and then this is going to be dx. So 1/2 base times height. The base is sine of x, and we're going to have to do a little bit of work for the height. Okay, so what I'm going to do is drop this height down. We're going to call that h. And that's going to make a right angle with the base. And now since this is equilateral, it means all of the sides are the same. So if this base is sine of x, that means all the other sides are also sine of x. So I know from here to here is sine of x. And since I dropped down the height and it's directly in the center, I know that this piece is 1/2 sine of x. This part from here to here is 1/2 sine of x. If the whole way across is sine of x, then this is 1/2. And so notice what we have here, I'll do color coding. We're going to look at this triangle. It is a right triangle. And so we can do Pythagorean theorem. So I'm going to do Pythagorean theorem to get the height. So it's going to be h squared plus 1/2 sine of x squared equals the hypotenuse squared. That'd be just sine of x squared. So again, it was a squared plus b squared equals c squared. And I'm doing that so that I can get the height. The height is going to go right here. Again, it's the area of the triangle. So 1/2 base times height. So I know this looks real scary, but we're just going to square stuff. 1/2 squared would be 1/4. And then we're also squaring sine. So I just squared everything that was in the parentheses. Basically just 2 squared is 4 is really all that we did there. And then equals sine squared. And we're trying to figure out height. So I want to subtract this over. So we have 1 sine squared minus 1/4 sine squared. So 1 minus 1/4 would be 3/4. sine squared. And then the last step is to square root. Now, usually you put plus and minus, but this is a height, it's a distance. We can't have a negative distance. We're just going to square root all of this. So square root of 3 is just square root of 3. There's not really anything I can do about that. Square root of 4 is 2. And then square root of sine squared would just be sine. This would be square root of 3 over 2 sine of x for our height. So again, this is 1/2 base times height. It's the area of the cross section. Now, this is not something I would make you do by hand. We're going to type this one later. And oftentimes for these cross sections, you do get to type them. All right, so we're going to do integral from 0 to pi. And then in here, we're going to have 1/2. And then times sine of x. And then times another fraction, square root of 3 over 2. Oops, that's not a square root. Ah, bring this back here. There we go. Square root of 3 over 2 sine of x dx. It's a lot to type. You type it exactly like it looks right here, but it's still a lot. So you have to get pi in there. There was a square root. There were a couple of fractions. And this will give us our answer. 0.680. All right, so again, what goes inside of the integral is the area of your shape. We had to fight a little bit for the height on that one, but it wasn't too bad. We got through. All right, number 3, the base of a solid is the region bounded by all these graphs. Cross sections are rectangles with heights that are twice the width, perpendicular. Oh, this says perpendicular to the y-axis. This is going to be a dy problem. All right, first, let's get the graph of the base of this here. So x cubed plus 1, it's a cubic graph moved up 1. We're going to go up 1 and put a point. And then I want some points on either side. So if I plug in 1, 1 plus 1 gives me 2. If I plug in -1, I'm going to get 0. This is going to wiggle like this. All right, y equals 0, that's just the x-axis, and then x equals 1 will be right here. So this is the area of the base of this 3-dimensional object. You're going to have to imagine the shapes coming up out of the paper. Now it says perpendicular to the y-axis. So this time all your slices, like a slice of bread, are going to go this way. And so immediately we need to rearrange the equations. This needs to be x equals instead of y equals. Like when you realize it's dy, stop what you're doing and rearrange those. Just do that first. So we would subtract over the 1, so be y minus 1 equals x cubed, and then cube root. So it's cube root of y minus 1 equals x. This is the equation that we're going to be using. So as soon as you realize it's dy, just go ahead and do that. All right, so let me draw my shape off to the side. It is a rectangle, and the base of it matches up with one of these slices, perpendicular to the y-axis. So the base of this is going to be right graph minus left graph. So instead of upper minus lower, now it's right minus left. So the right graph is this x equals 1. So our right graph is 1. And our left graph is this curve. So it's going to be 1 minus this. So again, it was right graph minus left graph. All right, and then you're ready to set up your integral. Now you have to use y values when you do your boundaries. This is a dy problem. So or actually, I can ask you guys that one. Look at your y-axis, guys. We're going to integrate from where to where. Look at the y values. What are going to be our boundaries for this one? I'll zoom in. I want to wait till I get a few more answers. So from here to here will give us from where to where. So good. It is going to be 0 to 2. right? 0 to 2. And inside of there, you're going to put the area of your shape. So area of a rectangle is base times height. So the base is this, 1 minus cube root of y minus 1. That's the base. Now the height, it says the height is 2 times the width. So the height is going to be 2 times this. And then dy at the end. So the base and the height, it's the same statement, but the height is 2 times the base. Now, don't worry, you would not have to do this one by hand either. We are going to type this in. And because I have this twice, I'm going to type it as squared. It's base times height, but they're the same except for that 2 in there. So, or you could type it all out twice. However, whatever's your personal preference. If you want to just save yourself some button pushing, you can do it as squared though, since there's 2 of them. All right, so integral 0 to 2. I'm going to put that 2 in there. That's right there. You can even put that 2 out front of the integral if you wanted, because it's a coefficient. You can kick it out. All right, and then we're going to have parentheses 1 minus cube root. So the cube root is in the math menu. That's where most everything is, right? Cube root. Now it says y minus 1. I'm still going to type x. Just shh, it'll be our little secret. The calculator will never know. It's just easiest because you have an x variable button. It's kind of like when it says t, we still type x. So I'm still going to type x just because that's easier. You could do alpha y, it's just more button pushing. All right, close parentheses, and you can either type that all over again or you can just hit squared because there's 2 of them. And then dx. Again, I know it says y. I'm just typing x. I have an x button. It's just more convenient. All right, and here's our answer. Eventually, it'll come up. I hope. There we go. 6.400. All right, number 4. The base of a solid is the region inside the circle. All right, let's review how to graph a circle real quick. It's going to be x squared plus y squared equals the radius squared. So this circle is centered at 0. It hasn't been altered at all, or I guess shifted is a better way to say that. If it was, like, for example, say you had x minus 1 squared plus y minus 3 squared equals the radius squared, your center would be at 1, 3, like it would be shifted, is all that happened there. This one just wasn't shifted. So it's going to be centered at 0, 0. So the origin is our center and the radius is 2. Again, this 4 is the radius squared. So 2 squared gives you 4. So we're centered at the origin, the radius is 2. And so our circle is going to look like this. All right, so cross sections, again, you have to imagine these shapes popping up out of the paper. Isosceles right triangles, or we're going to come back to that because that's a lot of vocabulary, with the hypotenuse on the base. Okay, so more vocabulary there. Again, we're going to come back to that. Perpendicular to the x-axis. All right, so that means that it is a dx problem. All of your slices are perpendicular to the x-axis. All right, so let's draw our shape off to the side. First of all, what's isosceles? I'll tell you if you've all forgotten, but I just want to throw the question out there and see if anyone knows what that means. If you have an isosceles triangle, what does that mean about the sides? It tells you something about the sides of the triangle. Oh, good, guys. Oh, nice job. Good job, guys. 2 sides are equal. You guys rock. Okay, 2 sides are the same. And if it's a right triangle, then it's going to be a 45, 45, 90 triangle. So you have 2 sides that are the same, and you've got a right angle in there. And it says the hypotenuse is on the base. So when you draw this, that means the hypotenuse is the bottom of it. So this is the hypotenuse. So this is going to be our right angle, and these 2 sides are the same. So this is what makes it isosceles. These 2 sides are the same. The hypotenuse is the base. That means the bottom of the triangle. So the hypotenuse is the part that matches up with this. Again, I get asked every time, Ms. Cole, why'd you draw it here? It doesn't matter. You could draw it anywhere. There's an infinite number of them. I'm just trying to show you that this matches up with upper graph minus lower graph. All right, now this one is a little tricky to get this because our equation is not set up y equals. We're going to have to rearrange this equation so that it is y equals. So I'm going to do this off to the side. I'm going to start by, this is algebra here. You're going to not be afraid of the algebra. We're going to subtract over the x squared. We'll have y squared equals 4 minus x squared. And then to get rid of the squared, you square root. Now we are going to get positive and negative. The positive square root is this half. So this upper part is going to be the positive square root of 4 minus x squared. And then this part down here, I'll kind of dot that one. That's going to be the negative square root. So the upper half of the circle, like this semicircle, that's the positive square root. The part underneath, that's the negative square root. So when you split it into the plus and minus, that's how that splits. All right, so now we are, I was going to say now we're ready to set up our integral, but we're not. We need to know what this base is. This base is upper graph minus lower graph. So it's going to be this minus this. So it'll be square root of 4 minus x squared minus negative square root of 4 minus x squared. Upper graph minus lower graph. Now that looks awful. I know you're like, oh my gosh, this is horrible. But the negatives cancel. So you're going to be adding. And one of them plus another one means that you have two of them. So it is 2 square root 4 minus x squared. So again, it was upper graph minus lower graph, negatives canceled, and we added them together, so we have 2 of them. So now we're ready to set up our integral. So this is a dx problem. It said perpendicular to the x-axis, so we're going to integrate from here to here. So that's -2 to +2. And then inside of there, you're going to put the area of your shape. So a triangle is 1/2 base times height. Then it'll be dx. So the base is this. That's what we just found, 2 square root of stuff. So that's the base. Now we need the height. So we are going to have to work again for this for a second, but I promise it's not going to be as bad as the other one. Okay, because this one's an isosceles right triangle, so you end up with all these similar triangles. If this entire base is 2 of these square roots, then halfway across is just one of them. I'm not going to try to label this because this is going to be way too much labeling and it's going to be like number explosion all over the place. But if the whole way across is 2 of the square roots, just halfway across is one of them. And because everything was the same in this triangle, because these sides were the same, if this is one of these square roots, then the height is one of those square roots as well. So it's just going to be square root 4 minus x squared. So the whole way across was 2 of them. The height is just going to be one of them. Now this one we will do by hand. I mean, like, Ms. Cole, this one looks awful. Again, it looks terrible, but it actually doesn't end up being so bad because the 1/2 and the 2 cancel. And then the roots also cancel. But if you have square root times another one, the roots are going to cancel because you're squaring it. The squared and the square root cancel out. It's kind of like square root of 5 times square root of 5 is just 5. Square root of all this stuff times square root of all this stuff is just going to be all that stuff. So the roots cancel out. So they're actually, after all of that, after fighting our way through all of this mess, the actual integral doesn't end up being too terrible. Right, so antiderivative is 4x then minus 1/3 x cubed from -2 to 2, upper boundary minus lower boundary. So if we plug in 2, that's going to be 8 minus 8/3. And if we plug in -2, that's going to be -8 plus 8/3. Negatives are going to cancel. -2 cubed would be -8, and those negatives cancel. So what I would do is distribute the negative sign. Because again, a lot of times stuff can either cancel out or combine together. And so 8 plus 8 would be 16. And then minus 8/3 and minus 8/3 would be minus 16/3. I'm going to go ahead and stop there. Again, not trying to torture you. If you had to get a common denominator there, 16 would be 48/3, and you could combine them together. All right, one more. Again, I was trying to do an example of like every type of shape that can happen. The base of a solid is the region bounded by, okay, this is going to be an upside down parabola moved up 1. So we're going to go up 1 and then plug in a few more points. So if we plug in 1, we're going to get 0. Same thing on the other side. And so here is our upside down parabola, or reflected parabola. All right, and then we've got x to the 4th minus 1. So that's going to move down 1. I'm going to put a point at 0, -1. And then if you plug in 1 to that, 1 to the 4th, 1 to any power is just going to be 1, minus 1 will be 0. So it's going to look also like a parabola. I know it's x to the 4th. It would be like a slightly narrower parabola. I know my picture is not, exactly perfect here, but you get something like that, which that just looks cool. And so here's the base of the 3-dimensional object that we're creating. So it says this time we want semicircles perpendicular to the x-axis. So again, that means going this way, it's going to be a dx problem. You have to envision these semicircles coming up out of the paper at you. And you have, an infinite number of them going this way. So I'm going to draw my shape off to the side. The base of it matches up with this here. And again, I could have drawn that highlighted thing anywhere. There's an infinite number of semicircles. And so this case, it is going to be upper graph minus lower graph. So the upper graph is the 1 minus x squared. And then minus the lower graph is the x to the 4th minus 1. So I'm just going to clean that up a little bit. We'll distribute the negative. And then the ones will combine together to give us 2. And then we're ready to set up the integral. So dx problem, you want to look at the x-axis. We're going to go from -1 to +1. And what goes in there is the area of the cross section. So it's the area of the shape. So area of a semicircle is 1/2 pi r squared. I just left a big space for the radius. It's 1/2 pi r squared. And you can put the 1/2 pi out front of the integral if you want. That's just a value, that's just a coefficient. So you can actually write it out here if you want. And here's the only common mistake I ever see with this. Semicircles usually go really well because it's 1/2 pi r squared. We do that a lot. Is that people will just take this and put it in there. What's the issue with that? Because this isn't the radius. What does this represent from here to here? Like if you just take that and put that in there, you kind of skipped one step. Good. That's the diameter. So what do I need to do with that to make it be the radius instead? Because I need for this to be r. I need for it to be the radius. Good. Half of, yep, good. Okay. So all you have to do is take that and divide it by 2. I think the reason people forget that is, number one, because we're human, because it's a lot, but also because there's already a half there. And so it feels like you already did a half, but that half is because this is a half circle. Like we don't have a full circle. That's what that half represents. This half is turning the diameter into a radius. So just make sure you put that there. Other than that, the semicircle ones usually go well. In fact, I maybe should have done this problem first. I think this is a good one to end on though, because it's an easier one. And we are not going to do that by hand. I'm going to type that. You cannot just make it 1/4. That's a good question though. The reason why is because this 2 would need to be squared. So that would be a 4th, and then a 4th times a half would be an 1/8. So I guess if you wanted to, if you don't like this, don't do this. You don't have to do this. I'm just answering the question. You could make it 1/8 pi, and then all of that squared. I kind of recommend against that. I feel like that's work that you don't have to do. But if you like that, and then you can, I like showing you your options. If you like that better, you can do that. My personal preference is I kind of don't, I'm a hands-off person. I would rather just sort of leave it like that. But 2 squared is 4. And then a 4th times a half would be an 8. So you can do it that way. All right, so I'm going to type in the original one. If you don't want to do that step, you don't have to, but you can feel like, oh, whoops. All right, so integral -1 to 1. And then we have 1/2 pi. And then inside the parentheses, we have -x squared minus x to the 4th plus 2. And we're having that to make it be a radius squared. So 1/2 pi r squared dx. And it will give us, oh, that happens fast, 1.934.